Hello, this is Kai Buzz. I'm trying to explain my indicator because everybody's interested on how it works. Well, this is gonna be a very in-depth topic, so if you don't have time to spend, I would recommend not sitting down and starting unless you are very interested in how all this works together. Um, so first off, um, let's just get into EMAs and wave functions, right? So what EMAs are and what all indicators are based off of on TradingView or anything like that are called wave functions, right? So if you have a wave function, that other wave function cancels one wave out and etc. It gets a little confusing, right? So I'm trying to break it down slowly, so just kind of keep an open mind here, because this is going to get really in depth. So here on the Dow Jones, I have placed a special set of EMAs or um, wave functions to display on the screen that I've selected from, math and mathematics and all that fun stuff. And we're going to get into the math later on. And what you're really trying to do when you set up an indicator. So, like I said, a wave function on an indicator is putting two waves together to create a wave cancellation and wave um, cancellation. See, this is confusing. So, wave goes, cancels, and then it. Ow, fuck. It's confusing. Alright, so it's really hard to explain as well because what a EMA is one wave function, right? Um so I keep saying wave function, but how this applies is really, really interesting because here on the weekly we have a set of EMAs that is our set frequency of wave functions that exist in reality that hold reality together. Wait, hold up. Confusing even more. We'll get into it. We're just trying to focus on looking at the relationship of a single wave pattern on the chart using EMAs. That's what we're doing. Alright, so let's go. Let's zoom out a little bit because this is a lot of data to load. So we're gonna zoom in or whatever you want to call it, and let's go to a day, right? So you see how these wave functions start to act, right? They are like support for the stock market, for the Dow Jones index, right? And they stay in the center of the chart, okay? This has to do with um, psychology and a bunch of unique properties that come along with these wave functions, right? So even if we go to like Bitcoin, right? Let's go to Bitcoin on the daily. Um, we can see these wave functions play an effect in how Bitcoin reacts and moves in the market, right? So these EMAs are kind of like the center line of the market. If the market's trading upwards or downwards, it'll always trade in the center of the market, okay? These EMAs will always stay in the center of the market. And you can go across any asset, and I mean, like, you can see XTZ doesn't show it on the daily because it's a newer asset and it's a smaller time frame. So let's go to 4 hours and you'll see those EMAs again appear on the screen. So you see how it just keeps bouncing off these wave functions and going back up into them, but at the same time as close this out. Okay. Because, where's my... Oh, I can't draw in here. Oh, it's so lame. Oh, wait, yeah, I can. Okay. So if the market's trading like this, right? These wave functions are going like this on the center of the chart, right? So if an asset is trading upwards, those center lines are moving up with the chart, right? And they fluctuate within the chart, okay? All the way, etc., right? Alright, so let me get this off. I don't know how to, there we go. Okay. Well, I can't delete it. So anyway, let's go over to Loom real quick and you can see these EMAs too. So here are the EMAs again. As you can see, it's trading up back into the center line of the moving averages. Okay. Alright, let me close this out. And oh, I shouldn't have done that. Oh, I'll come back to it. Okay. So going back to the EMA part, right? So here's a typical wave function, right? Up, down, up. That's a wave function. All things are waves, pretty much. All matter. We'll get into that later. And close that so I'm not using my resources. And let's go here. Okay, and this is what a typical indicator is doing, is it's measuring one wave function with another wave function, okay? So you see the first wave function with the secondary wave function, we call this a signal, okay? That's how indicators work. They're measuring the crosses between these two wave functions. And it's a very unique and interesting thing how these work because it all comes down to math. Alright, now we got that out of the way. Let's go to... gotta close this. And then let's open this right here. So, how would I describe this? Because this is a very complex topic and it's a multi-dimensional answer. So we just saw how that sequence of wave functions that traders chart on or plot on charts is important, right? But going into how the wave function actually functions in relation to reality, and how these all intertwine is very complex. So let's say that you have uh, let's say you have a wall, right? The wall is made up of, let's say, wood, okay? So that wood has its own wave function to exist in reality, right? It's a wave, right? The matter is in a wave format, all right? Or fluctuation. Then let's say you paint it, right? Well, that paint is going to have its own wave pattern, but yet those two wave patterns are held or make up an object, one the solid object being the wood, and then the object on top of that object is the paint, right? And these two wave functions sit together. Well, there has to be some kind of wave function that goes through these objects that keep them together. And that would be basically the EMAs that a lot of traders use to chart and watch the momentum of the chart and how these wave functions are starting to or help dictate where the market is going, right? And a lot of traders don't understand the importance of understanding why these wave functions that exist in reality, how they exist through matter as well. All right, that's what you're measuring with the indicators, okay? And another example would be on why this is a multi-dimensional kind of answer is because it's not as simple as giving, a one explanation to how it works. It's math in multiple layers, because if you take reality, like I just described with the painted wall, there's two different wave functions that make that work and that keep it, and another wave function that goes through the center and keeps it together. And traders are very, very keen to this relationship. They're just not aware of how it works, or have a very little understanding of how it works. So going into the multi-layered wave function, let's talk about the layered, or the layers, or the concept of layers of waves, right? So here we have an egg, all right? You can see the different layers as we go and go and go, and different layers and different layers. We've got, the yolk, and then it's layers of within it, right? And then on the outside, it's got its outer layer, and another layer, and another layer, right? And this is how atoms are structured, like molecules and everything are structured, right? It looks similar to this, right? And this structure keeps repeating through nature, and it's a very important structure. It's because if you were to stack all matter into reality and make it work, you have to put it in cylinders, okay? Or I'm sorry, spheres, right? You have to stack spheres together, right? That's why we have spheres inside of spheres inside of spheres, right? Yolk, whatever that's supposed to be. Oh, or is it fibril layer, right? All these different layers are all different wave functions stacked on top of each other, okay? And if you were to stack wave functions, you would need to stack them in, or display that in a sphere, okay? And it's not just going down to like simple things like an egg. We're talking about planet Earth. Like, it's also layered in spheres, right? All the way to the atmosphere. Okay, the layers of the atmosphere, right? Um, then if you look at a human embryo with sperm, you see that spherical layering to reality, right? And again, what you're measuring with EMAs is that center line through these wave functions that are stacked on top of each other. Okay, so center line wave function through layered wave functions. Okay, so it's a multi-dimensional answer to how this all works. Um, and it's not very easy to describe, and I'm trying to do my best to describe it, because another thing is a lot of information is lost in the interpretation of language, because language actually can't really describe complex um, relations, and that's why it's hard to understand, um, certain concepts with math and physics and all kinds of stuff, right? Um, so let's see, what do we got to go over next? Let's go over to um, I don't know. Let's do the math video. So I'm gonna step away from the computer. I'm gonna get 3 videos loaded up on the screen to play of the best kind of examples I've been able to find. Let's load this up. Alright. Sorry, I gotta play with my screen a little bit because I can't have all this stuff loaded in the background ready to go and be able to go through it. Let's show playlist. Okay. And I'd actually take back, I'm gonna play one video and I'm gonna step away and after I play two videos. So let's do this one. Y'all, we want the helical model, and then we want I think this is it, right? Helical, brave. No. Okay, so prime numbers. Okay. Alright, so I just want to show another type of a four-dimensional kind of relation with what I'm describing. So let me go ahead and mute myself, and you're not going to hear me for a while. So desktop. Okay, wait, I gotta explain this video. Sorry. Alright, so here we have the helical model. This is how the planets rotate around the sun. And think on the relationship between these EMAs and the planet. The EMAs being the sun and the chart being the planet, right? So the EMAs that traders are famous for using are doing what the sun's doing, and then the planets that are rotating around the sun is what the chart's doing, right? That right there is a very interesting topic, okay? And it fascinates me. This is why I love trading and being able to use these tools to understand relationships. It's beyond fascinating to me. I love it. Okay, so let me go and place this on stop, and I'm now gonna mute myself and let a mathematician explain pi and quaternions, and you'll start to get even more confused. Alright, I'll be back in a while.
What you're looking at right now is something called Quaternion multiplication. Or rather, you're looking at a certain representation of a specific motion happening on a four-dimensional sphere. What you're looking at right now is something called Quaternion multiplication. Or rather, you're looking at a certain representation of a specific motion happening on a four-dimensional sphere being represented in our three-dimensional space, one which you'll understand by the end of this video. Quaternions are an absolutely fascinating and often underappreciated number system from math. Just as complex numbers are a two-dimensional extension of the real numbers, quaternions are a four-dimensional extension of complex numbers. But they're not just playful mathematical shenanigans. They have a surprisingly pragmatic utility for describing rotation in three dimensions, and even for quantum mechanics. The story of their discovery is also quite famous in math. The Irish mathematician William Rowan Hamilton spent much of his life seeking a three-dimensional number system, analogous to the complex numbers. And as the story goes, his son would ask him every morning whether or not he had figured out how to divide triples, and he would always say, "No, not yet." But on October 16, 1843, while crossing the Broom Bridge in Dublin, he realized, with a supposed flash of insight, that what he needed was not to add a single dimension to the complex numbers, but to add 2 more imaginary dimensions. 3 imaginary dimensions describing space, and the real numbers, sitting perpendicular to that in some kind of 4th dimension. He carved the crucial equation describing these 3 imaginary units into the bridge, which today bears a plaque in his honor showing that equation. Now, you have to understand, our modern notion of vectors with their dot product and the cross product and things like that didn't really exist in Hamilton's time, at least not in a standardized form. So after his discovery, he pushed hard for quaternions to be the primary language with which we teach students to describe 3-dimensional space, even forming an official quaternion society to proselytize his discovery. Now, unfortunately, this was balanced with mathematicians on the other side of the fence, who believed that the confusing notion of quaternion multiplication was not necessary for describing 3 dimensions, resulting in some truly hilarious old-timey trash talk legitimately calling them evil. It's even believed that the Mad Hatter scene from Alice in Wonderland, whose author you may know was an Oxford mathematician, was written in reference to quaternions, that the chaotic table placement changes were mocking their multiplication, and that certain quotes were referencing their non-commutative nature. Fast forward about a century, and the computing industry gave quaternions a resurgence among programmers who work with graphics and robotics and anything involving orientation in 3D space. And this is because they give an elegant way to describe and to compute 3D rotations, which is computationally more efficient than other methods, and which also avoids a lot of the numerical errors that arise in these other methods. The 20th century also brought quaternions some more love from a completely different direction, quantum mechanics. You see, the special actions that quaternions describe in 4 dimensions are actually quite relevant to the way that 2-state systems, like spin of an electron or the polarization of a photon, are described mathematically. What I'll show you here is a way to visualize quaternions in their full 4-dimensional glory. It would surprise me if this approach was fully original, but I can say that it's certainly not the standard way to teach quaternions, and that the specific 4-dimensional right-hand rule image that I'd like to build up to is something that I haven't really seen elsewhere. Building up an understanding for this visual will take us meaningful time, but once you have it, there is a very natural and satisfying intuition for how to think about quaternion multiplication. It won't be until the next video that I show you how exactly quaternions describe orientation in 3 dimensions, which is, for some people, the whole reason we care about it. But once we're able to go at it armed with the image of what they're doing to a 4D hypersphere, there's a pleasing understanding to be had for the otherwise opaque formulas characterizing this relationship. The structure here will be to start by imagining teaching complex numbers to someone who only understands 1 dimension, then describing 3D rotations to someone who only understands 2 dimensions, and ultimately to represent what quaternions are doing up in 4 dimensions within the constraints of our 3D space. Our first character is Linus the Linelander, whose mind can only grasp the 1-dimensional geometry of lines and the algebra of real numbers. We're going to try to describe complex numbers to Linus, and it's really important for you to empathize with him as much as you can during this, because in a few minutes, you're going to be in his shoes. On the one hand, you could define complex numbers purely algebraically. You say each one is expressed as some real number plus some other real number times I, where I is a newly invented constant whose defining property is that I times I equals -1. Then you say to Linus, to multiply 2 complex numbers, you just use the distributive property, what many people learn in school as FOIL, and you apply this rule that I times I equals -1 to simplify things down further. And that's fine, that totally works, and the standard textbook way to introduce quaternions is analogous to this, showing the algebraic rules and calling it done. But I think something is missing if we don't at least try to show Linus the geometry of complex numbers and what complex multiplication looks like, since the problems in math and physics where complex numbers are shockingly useful often leverage this spatial intuition. You and I, who understand 2 dimensions, might think of it like this. When you multiply 2 complex numbers, z times w, you can think of z as a sort of acting on w, rotating and stretching it in some way. I like to think of this by broadening the view and asking, what does z do to the entire plane? And you can think of that bird's eye view action by imagining using one hand to fix the number 0 in place, and using another hand to drag the point at 1 up to z, since anything times 0 is 0, and anything times 1 is itself. And in 2 dimensions, there is one and only one stretching rotating action on the plane that'll do this. This is also how I'll have you thinking about Quaternion multiplication later on, where the number on the left acts as a kind of function to the one on the right, and we'll understand this function by seeing how it acts by transforming space, although instead of rotating 2D space, it does a sort of double rotation in 4D space. By the way, if you want to review thinking about complex numbers as a kind of action, a good warm-up for this video might be the one I did on e to the pi I, explained with introductory group theory. Now, Linus the Linelander is pretty comfortable with the idea of stretching. That's what multiplication by real numbers looks like. Maybe it's a little weird for him to think about stretching in multiple dimensions, but it's not fundamentally different. The difficult thing to communicate to Linus is rotation. Specifically, focus on the unit circle of the complex plane, all the numbers a distance 1 from 0, since multiplication by these numbers corresponds to pure rotation. How would you explain to Linus the look and the feel of multiplying by these numbers? At first, that might seem impossible. I mean, rotation is just such an intrinsically two-dimensional idea. But, on the other hand, rotation involves only one degree of freedom. A single number, the angle, specifies a given rotation uniquely. So, in principle, it should be possible to associate the set of all rotations to the one-dimensional continuum that is Linus's world. And there are many ways you could do this, but the one I'm going to show you is what's called a stereographic projection. It's a special way to map a circle onto a line, or a sphere into a plane, or even a 4D hypersphere into 3D space. For every point on the unit circle, draw a line from -1 through that point, and wherever it intersects the vertical line through the circle's center, that's where the point of the circle gets projected. So, for example, the point at 1 gets projected into the center of the line. The point I actually stays fixed in place, as does -I. All of the points on that 90-degree arc between 1 and I will get projected somewhere in the interval between where 1 landed and where I landed. As you continue farther around the circle on the arc between I and -1, the projected points end up farther and farther away at an increasing rate. Similarly, if you come around the other way towards -1, the projected points end up farther and farther on the other end of the line. This line of projected points is what we show to Linus, labeling a few key points, like 1 and I and -1 all for reference. Technically, the point at -1 has no projection under this map, since the tangent line to the circle at that point never crosses the vertical line. But what we say is that -1 ends up at the point at infinity. This is a special point you imagine adding to the line, where you would approach it if you walk infinitely far along the line in either direction. Now, it's important to remember, and to remind Linus, that what he's seeing is only the complex numbers that are a distance 1 from the origin, the unit circle. Linus doesn't see most numbers, like 0 or 1 plus I or -2 minus I, but that's okay, because right now we just want to describe complex number z, where multiplying by z has the effect of a pure rotation, so he only needs to understand the unit circle. For example, when we take the number I and multiply it by any other complex number w, the effect is to rotate by 90 degrees counterclockwise. And when we apply this action to the circle being projected down to the line for Linus, what does he see? Well, it's a bit of a strange morphing action on the line, one which I want you to become familiar with for something we'll see later on. It's easiest to understand by following a few key reference points. I times 1 is I, so that means the number 1 should move up to I. I times I is -1, so the point at I slides off to infinity. I times -1 is equal to -I, so that point at infinity kind of comes back around from the bottom to the position 1 unit below the center. And I times -I is 1, so that point at -I slides up to 1. Even though this is kind of a weird motion, it lets us communicate some important ideas to Linus. For example, multiplying by I 4 times, which corresponds to rotating by 90 degrees 4 times in a row, gets us back to where we started. I to the 4th equals 1. Here, to get more of a feel for things, let me just show the circle rotated at various different angles. On both the left and the right half of the screen here, I'm putting a hand on the point that started at the number 1 to help us and to help Linus keep track of the overall motion. Next, let's introduce Felix the Flatlander, who only understands two-dimensional geometry. Imagine trying to explain rotations of a sphere to Felix. In the spirit of transitioning from complex numbers to quaternions, let's extend the complex numbers with its horizontal axis of real numbers and its vertical axis of imaginary numbers with a third axis, defined by some newly invented constant, j, sitting 1 unit away from 0, perpendicular to the complex plane. Instead of having this new axis in the z direction, like you might expect, for a better analogy with how we'll visualize quaternions, we'll want to orient things so that the I and the j axes sit in the x and the y directions, with the real number line aligned along the z direction. So every point in 3D space is described as some real number plus some real number times I plus some real number times j. As it happens, it's not possible to define a notion of multiplication for a 3D number system like this that would satisfy the usual algebraic properties that make multiplication a useful construct. Perhaps I'll outline why this is the case in a follow-on video, but staying focused on our current goal, think about describing 3D rotations in this coordinate system to Felix the Flatlander. The unit sphere consists of all those numbers which are a distance 1 from 0 at the origin, meaning the sum of the squares of their coordinates is 1. We can't show all of 3D space to Felix, but what we can do is project this 2D surface to him and give him a feel for what reorientations of the sphere look like under that projection. Analogous to what we did before, stereographic projection will associate almost every point on the unit sphere with a unique point on the horizontal plane defined by the I and the j axes. For each point on the sphere, draw a line from -1 at the south pole through that point and see where it intersects the plane. So the point 1 at the North Pole ends up at the center of the plane. All of the points of the Northern Hemisphere get mapped somewhere inside the unit circle of the ij plane. And that unit circle, which passes through ij, -I, and -j, actually stays fixed in place. And that's an important point to make note of. Even though most points and lines and patches that Felix the Flatlander sees are going to be warped projections of the real sphere, this unit circle is the one thing that he has which is an honest part of our unit sphere, unaltered by projection. All of the points in the southern hemisphere get projected outside that unit circle, each getting farther and farther away as you approach -1 at the south pole. And again, -1 has no projection under this mapping, but what we say is that it ends up at some point at infinity. That point at infinity is something such that no matter which direction you walk on the plane, as you go infinitely far out, you'll be approaching that point. It's analogous to how if you walk any direction away from the North Pole, you're approaching the South Pole. Now let me just pull up a view of what Felix sees in 2 dimensions. As I rotate the sphere in various ways, the lines of latitude and longitude drawn on that sphere get projected into various circles and lines in Felix's space. And the way I've done things up here, the checkerboard pattern on the surface of the sphere is accurately reflected in the projected view that you see with Felix. And the pink dot represents where the point that started at the North Pole ends up after the rotation. And that yellow circle represents where the equator ended up after the projection. The more you put yourself in Felix's shoes right now, the easier quaternions will be in a moment. And as with it helps to focus on a few key reference objects rather than trying to see the whole sphere. This circle, passing through 1, I, -1, and -I, gets mapped onto a line which Felix sees as the horizontal axis. It's important to remind Felix that what he sees is not the same thing as the I-axis. Remember, we're only projecting the numbers that have a distance 1 from the origin, so most points on the actual I-axis, like 0 and 2i and 3i, etc., are completely invisible to Felix. Similarly, the circle that passes through 1, j, -1, and -j gets projected onto what he sees as a vertical line. And in general, any line that Felix sees comes from some circle on the sphere that passes through -1. In some sense, a line is just a circle that passes through the point at infinity. Now think about what Felix sees as we rotate the sphere. A 90-degree rotation about the j-axis brings 1 to I to -1, -1 to -I, and -I to 1. So what Felix the Flatlander sees is an extension of the rotation that Linus the Linelander was seeing. Notice also that this action rotates the ij unit circle to the position where the 1j unit circle used to be. So what Felix sees is his yellow unit circle getting transformed into a vertical line, while that red vertical line gets transformed into the unit circle. Of course, from our perspective, we know this is all just rigid motion. No actual stretching or morphing is taking place. All of that is just an artifact of the projection. Similarly, a rotation about the I-axis involves moving 1 to j, j to -1, -1 to -j, and -j to 1. This rotation turns the ij unit circle into the 1i unit circle, which to Felix looks like the unit circle getting transformed into a horizontal line. Where the only points staying fixed in place are 1 at the origin and -1 off at infinity. In the same way that the complex numbers included the real numbers with a single extra quote-unquote imaginary dimension, represented by the unit I, and that the not actually a number system thing we had in 3 dimensions included a second imaginary direction, j, the quaternions include the real numbers together with 3 separate imaginary dimensions, represented by the units I, j, and k. Each of these 3 imaginary dimensions is perpendicular to the real number line, and they're all perpendicular to each other, somehow. So, in the same way that complex numbers are represented as a pair of real numbers, each quaternion can be written using 4 real numbers, and it lives in 4-dimensional space. You often think of this as being broken up into a real or scalar part, and then a 3D imaginary part. And Hamilton used a special word for quaternions that had no real part and just ijk components, a word which was previously somewhat foreign in the lingo of math and physics: vector. On the one hand, you could just define quaternion multiplication by giving the rules for how I, j, and k multiply together, and saying that everything must distribute nicely. This is analogous to defining complex multiplication by saying that I times I is -1, and then distributing and simplifying products. And indeed, this is how you would tell a computer to perform quaternion multiplication, and the relative compactness of this operation, compared to, say, matrix multiplication, is what's made quaternions so useful for graphics programming and many other things. There's also a rather elegant form of this multiplication rule written in terms of the dot product and the cross product, and in some sense, quaternion multiplication subsumes both of these notions, at least as they appear in 3 dimensions. But just as a deeper understanding for complex multiplication comes from understanding its geometry, that multiplying by a complex number involves a combination of scaling and rotating, you and I are here for the 4-dimensional geometry of quaternion multiplication. And just as the magnitude of a complex number, its distance from 0, is the square root of the sum of the squares of its component, that same operation gives you the magnitude of a quaternion. And multiplying one quaternion, q1, by another, q2, has the effect of scaling q2 by the magnitude of q1, followed by a very special type of rotation in 4 dimensions. And those special 4D rotations, the heart of what we need to understand, correspond to the hypersphere of quaternions, a distance 1 from the origin, both in the sense that the quaternions whose multiplying action is a pure rotation live on that hypersphere, and in the sense that we can understand this weird 4D action just by following points on the hypersphere, rather than trying to look at all of the points in the inconceivable stretches of 4-dimensional space. Analogous to what we did for Linus and Felix, we stereographically project this hypersphere into 3D space. This label in the upper right is going to show a given unit quaternion, and this little pink dot will show where that particular quaternion gets projected in our 3D space. Just as before, we're projecting from the number -1, which sits on the real number line that is somehow perpendicular to all of our 3D space and beyond our perception. Just as before, the number 1 ends up projected straight into the center of our space. And in the same way that I and negative I were fixed in place for Linus, and that the ij unit circle was fixed in place for Felix, we get a whole sphere passing through ij and k on that unit hypersphere, which stays in place under the projection. So what we see as a unit sphere in our 3D space represents the only unaltered part of the hypersphere of quaternions getting projected down onto us. It's something analogous to the equator of a 3D sphere, and it represents all of the unit quaternions whose real part is 0, what Hamilton would have described as unit vectors. The unit quaternions with positive real parts, between 0 and 1, end up somewhere inside this unit sphere, closer to the number 1 in our 3D space, which should feel analogous to how the northern hemisphere got mapped inside the unit circle for Felix. On the other hand, all the unit quaternions with negative real part end up somewhere outside that unit sphere. The number -1 is sitting off at the point at infinity, which you can easily find by walking in any direction. Keep in mind, even though we see the projection of some of these quaternions as being closer or farther from the origin of our 3D space, everything you're looking at represents a unit quaternion. So everything you're looking at really has the same magnitude, the same distance from the number 0. And that number 0 itself is nowhere to be found in this picture. Like all other non-unit quaternions, it's invisible to us. In the same way that for Felix, the circle passing through 1, I, -1, and -I got projected into a line through the origin, when we see this line through the origin passing through I and -I, we should understand that it really represents a circle. Likewise, up on the hypersphere, invisible to us, there is a unit sphere passing through 1, I, j, -1, -I, and -j. And that whole sphere gets projected into the plane that we see passing through 1, I, -I, j, -j, and -1 off at infinity, what you and I might call the xy plane. In general, any plane that you see here really represents the projection of a sphere somewhere up on the hypersphere which passes through the number -1. Now the action of taking a unit quaternion and multiplying it by any other quaternion from the left can be thought of in terms of two separate 2D rotations, happening perpendicular to and in sync with each other, in a way that could only ever be possible in 4 dimensions. As a first example, let's look at multiplication by I. We already know what this does to the circle that passes through 1 and I, which we see as a line. 1 goes to I goes to -1 off at infinity, -1 comes back around to -I, and -I goes to 1. Remember, just like what Linus saw, all of this is the stereographic projection of a 90-degree rotation. Now look at the circle passing through j and k, which is in a sense perpendicular to the circle passing through 1 and I. Now it might feel weird to talk about two circles being perpendicular to each other, especially when they have the same center, the same radius, and they don't touch each other at all, but nothing could be more natural in 4 dimensions. You can think of the action of I on this perpendicular circle as obeying a certain right-hand rule. If you'll excuse the intrusion of my ghostly green screen hand into our otherwise pristine Platonic mathematical stage, you let that thumb of your right hand point from the number 1 to I, and you curl your fingers. The JK circle will rotate in the direction of that curl. How much? Well, by the same amount as the 1I circle rotates, which is 90 degrees in this case. This is what I meant by two rotations perpendicular to and in sync with each other. So j goes to k goes to -j, -j goes to -k, and -k goes to j. This gives us a little table for what the number I does to the other quaternions. But I want this not to be something that you memorize, but something that you could close your eyes and you could really see. Computationally, if you know what a quaternion does to the numbers 1, I, j, and k, you know what it does to any arbitrary quaternion, since multiplication distributes nicely. In the language of linear algebra, 1, I, j, and k form a basis of our 4-dimensional space, so knowing what our transformation does to them gives us the full information about what it does to all of space. Geometrically, a four-dimensional creature would be able to look at those two perpendicular rotations that I just described and understand that they lock you into one and only one rigid motion for the hypersphere. We might lack the intuitions of such a hypothetical creature, but we can maybe try to get close. Here's what the action of repeatedly multiplying by I looks like on our stereographic projection of the IJK sphere. It gets rotated into what we see as a plane, then gets rotated further back to where it used to be, though the orientation is all reversed now. Then it gets rotated again into what we see as a plane, and after the fourth iteration, it ends up right back where it started. As another example, think of a quaternion like q equals negative square root of 2 over 2 plus square root of 2 over 2 times I, which, if we pull up a picture of a complex plane, is a 135-degree rotation away from 1 in the direction of I. Under our projection, we see this along the line from 1 to I, somewhere outside the unit sphere. If that sounds weird, just remember how Linus would have seen this same number. The action of multiplying this q by all other quaternions will look to us like dragging the point at 1 all the way to this projected version of q, while the jk circle gets rotated 135 degrees, according to our right-hand rule. Multiplication by any other quaternion is completely similar. For example, let's see what it looks like for j to act on other quaternions by multiplication from the left. The circle through 1 and j, which we see projected as a line through the origin, gets rotated 90 degrees, dragging 1 up to j. So j times 1 is 1, and j times j is negative 1. The circle perpendicular to that one, passing through I and k, gets rotated 90 degrees according to this right-hand rule, where you point your thumb from 1 to j. So j times I is negative k, and j times k is I. In general, for any other unit quaternion you see somewhere in space, start by drawing the unit circle passing through 1, q, and negative 1, which we see in our projection as a line through the origin. Then draw the circle perpendicular to that one on what we see as the unit sphere. You rotate the first circle so that 1 ends up where q was, and rotate the perpendicular circle by the same amount according to the right-hand rule. One thing worth noticing here is that order of multiplication matters. It's not, as mathematicians would say, commutative. For example, I times j is k, which you might think of in terms of I acting on the quaternion j, rotating it up to k. But if you think of j as acting on I, j times I, it rotates I to negative k. In fact, commutativity, this ability to swap the order of multiplication, is a way more special property than a lot of people realize. And most groups of actions on some space don't have it. It's like how in solving a Rubik's Cube, order matters a lot. Or how rotating a cube about the z-axis and then about the x-axis gives a different final state from rotating it about the x-axis then about the z-axis. And last, as one final but rather important point, so far I've shown you how to think about quaternions as acting by left multiplication, where when you read an expression like I times j, you think of I as a kind of function morphing all of space, and j is just one of the points that it's acting on. But you can also think of them as a different sort of action, by multiplying from the right, where in this expression, j would be acting on I. In that case, the rule for multiplication is very similar. It's still the case that 1 goes to j and j goes to negative 1, etc., but instead of applying the right-hand rule to the circle perpendicular to the 1j circle, you would use your left hand. So either way, I times j is equal to k, but you can either think about this with your right hand curling the number j to the number k as your thumb points from 1 to I, or as your left hand curling I to k as its thumb points from 1 to j. Understanding this left-hand rule for multiplication from the other side will be extremely useful for understanding how unit quaternions describe rotation in 3 dimensions. And so far, it's probably not clear how exactly quaternions do describe 3D rotation, I mean, if you consider one of these actions on the unit sphere, passing through I, J, and K, it doesn't leave that sphere in place. It morphs it out of position. So the way that this works is slightly more complicated than a single quaternion product. It involves a process called conjugation, and I'll make a full follow-on video all about it so that we have the time to go through some examples. In the meantime, for more information on the story of quaternions and their relation to orientation in 3D space, Quanta, a mathematical publication I'm sure a lot of you are familiar with, just put out a post in a kind of loose conjunction with this video. Link in the description. If you enjoyed this, consider sharing it with some friends. And if you felt like the narrative structure here was actually helpful for understanding, maybe reassure those friends who would be turned off by a large timestamp that good math is actually worth the time. And many thanks to the patrons.
Alright, so that's layer pretty much 1 of how the indicator works. It creates a hypersphere, and then also it creates a another relation, which is very interesting, and I'm just now starting to dive into how all these relations work and how it functions. And then the difficult part would be to really program it, because like as a bot to trade with, because it's using such a complex structure. And this is what a lot of traders fail to understand about how these moving averages work and these indicators work, is because they're they're based off of wave functions, and these wave functions, these traders are looking for these cancellations, causes in the wave function, um, to cause these changes in the market, or to help define when the market shifts in momentum. So the second part, which I have pretty much done in the indicator, would be more
The full
in
title of
this
this video
video.
might be something like,
So
How Pretty But Pointless
let me mute myself again. Let him describe it, because I don't have time to make a video like this. Like, I'm definitely giving a shout out in the description on this guy. He's amazing. Appreciate the video.
patterns and polar plots of primes prompt pretty important ponderings on properties of those primes. I first saw this pattern that I'm about to show you in a question on the Math Stack Exchange. It was asked by a user under the name Dwymark and answered by Greg Martin, and it relates to the distribution of prime numbers together with rational approximations for pi. You see, what the user had been doing was playing around with data in polar coordinates. As a quick reminder, so we're all on the same page, this means labeling points in
Sorry. This this video also helps describe why pi and Fibonacci is also very important in charting. If you trade Bitcoin, you notice it very well. This is why, and then this is another layer on top of the hypersphere, and if it's hard, trust me. It's a multi-dimensional kind of thing. So this video explains why pi is important in charting as well. So I'm gonna mute myself and continue with the video.
2D space, not with the usual xy coordinates, but instead with a distance from the origin, commonly called r for radius, together with the angle that that radial line makes with the horizontal, commonly called theta. And for our purposes, this angle will be measured in radians, which basically means that an angle of pi is halfway around, and then 2 pi is a full circle. And notice, polar coordinates are not unique in the sense that adding 2 pi to that second coordinate doesn't change the location that this pair of numbers is referring to. The pattern that we'll look at centers around plotting points where both of these coordinates are a given prime number. There is no practical reason to do this. It's purely fun. We're just frolicking around in the playground of data visualization. And to get a sense for what it means, look at all the whole numbers rather than just the primes. The point 1, 1 sits a distance 1 away from the origin with an angle of 1 radian, which actually means this arc is the same length as that radial line. And then 2, 2 has twice that angle and twice the distance. And to get to 3, 3, you rotate 1 more radian with a total angle that's now slightly less than a half turn, since 3 is slightly less than pi, and you step 1 unit farther away from the origin. I really want you to make sure that it's clear what's being plotted, because everything that follows depends on understanding it. Each step forward is like the tip of a clock hand, which rotates 1 radian with each tick, a little less than a sixth of a turn, and it grows by 1 unit at each step. As you continue, these points spiral outwards, forming what's known in the business as an Archimedean spiral. Now, if you make the admittedly arbitrary move to knock out everything except the prime numbers, it initially looks quite random. After all, primes are famous for their chaotic and difficult to predict behavior. But when you zoom out, what you start to see are these very clear galactic-seeming spirals. And what's weird is some of the arms seem to be missing. And zooming out even further, those spirals give way to a different pattern. These many different outward-pointing rays. And those rays seem to mostly come in clumps of 4, but there's the occasional gap, like a comb missing its teeth. The question for you and me, naturally, is what on earth is going on here? Where do these spirals come from, and why do we instead get straight lines at this larger scale? If you wanted, you could ask a more quantitative question, and count that there are 20 total spirals. And then up at that larger scale, if you patiently went through each ray, you'd count up a total of 280. And so this adds a further mystery of where these numbers are coming from, and why they would arise from primes. Now this is shocking, and beautiful, and you might think that it suggests some divine hidden symmetry within the primes. But to steady your expectations, I should say that the fact that the person asking this question on Math Exchange jumped right into prime numbers makes the puzzle a little misleading. If you look at all of the whole numbers, not just the primes, as you zoom out, you see very similar spirals. They're much cleaner, and now there's 44 of them instead of 20, but it means that the question of where the spirals come from is, perhaps disappointingly, completely separate from the question of what happens when we limit our view to primes. But don't be too disappointed, because both these questions are still phenomenal puzzles. There's a very satisfying answer for the spirals, and even if the primes don't cause the spirals, asking what goes on when you filter for those primes does lead you to one of the most important theorems about the distribution of prime numbers, known in number theory as Dirichlet's theorem. To kick things off, let's zoom back in a little bit smaller. Did you notice that as we were zooming out, there were these 6 little spirals? This offers a good starting point to explain what's happening in the 2 larger patterns. Notice how all the multiples of 6 form one arm of this spiral. Then the next one is every integer that's 1 above a multiple of 6. And then after that, it includes all the numbers 2 above a multiple of 6, and so on. Why is that? Well, remember that each step forward in this sequence involves a turn of 1. Since all of those multiple of 6, about it. A prime number can't be a multiple of 6, and it also can't be 2 above a multiple of 6 unless it's 2, or 4 above a multiple. So, at least at this smaller scale, nothing magical is going on. And while we're in this simpler context, let me introduce some terminology that mathematicians use. Each one of these sequences, where you're counting up by 6, is fancifully called a residue class mod 6. The word residue here is sort of an overdramatic way of saying remainder, and mod means something like where the thing you divide by is. So, for example, 6 goes into 20 3 times, and it leaves a remainder of 2. so 20 has a residue of 2 mod 6. Together with all the other numbers, leaving a remainder of 2 when the thing you divide by is 6, you have a full residue class mod 6. I know that that sounds like the world's most pretentious way of saying everything 2 above a multiple of 6, but this is the standard jargon, and it is actually handy to have some words for the idea. So, looking at our diagram, in the lingo, each of these spiral arms corresponds to a residue class mod 6, and the reason we see them is that 6 is close to 2 pi. Turning 6 radians is almost a full turn. And the reason we see only 2 of them when filtering for primes is that all prime numbers are either 1 or 5 above a multiple of 6, with the exceptions of 2 and 3. With all that as a warm-up, let's think about the larger scale. In the same way that 6 steps is close to a full turn, taking 44 steps is very close to a whole number of turns. Here, let's compute it. There are 2 pi radians per rotation, right? So taking 44 steps, turning 44 radians, gives a total of 44 divided by 2 pi rotations, which comes out to be just barely above 7 full turns. You could also write this by saying that 44/7 is a close approximation for 2 pi, which some of you may better recognize as the famous 22/7 approximation for pi. What this means is when you count up by multiples of 44 in the diagram, each point has almost the same angle as the last one, just a little bit bigger. So as you continue on with more and more, we get this very gentle spiral as the angle increases. That 7 radian counterclockwise. Same for everything 2 above a multiple of 44, and so on, eventually filling out the full diagram. To phrase it with our fancier language, each of these spiral arms shows a residue class mod 44. And maybe now you can tell me what happens when we limit our view to prime numbers. Primes cannot be a multiple of 44, so that arm won't be visible. Nor can a prime be 2 above a multiple of 44, or 4 above, and so on, since all those residue classes have nothing but even numbers. Likewise, any multiples of 11 can't be prime, except for 11 itself, so the spiral of numbers 11 above a multiple of 44, they won't be visible, and neither will the spiral of numbers 33 above a multiple of 44. This is what gives the picture those Milky Way-seeming gaps. Each spiral we're left with is a residue class that doesn't share any prime factors with 44. And within each one of those arms that we can't reject out of hand, the prime numbers seem to be sort of randomly distributed. And that's a fact that I'd like you to tuck away. We'll return to it later. This is another good chance to inject some of the jargon that mathematicians use. What we care about right here are all the numbers between 0 and 43 that don't share a prime factor with 44, right? The ones that aren't even and they also aren't divisible by 11. When two numbers don't share any factors like this, we call them relatively prime, or also co-prime. In this example, you could count that there are 20 different numbers between 1 and 44 that are co-prime to 44. And this is a fact that a number theorist would compactly write by saying phi of 44 equals 20, where the Greek letter phi here refers to Euler's totient function, yet another needlessly fancy word, which is defined to be the number of integers from 1 up to n which are co-prime to n. It comes up enough that it's handy to have compact notation. More obscurely, and I had never heard this before, but I find it too delightful not to tell, these numbers are sometimes called the totatives of n. Back to the main thread. In short, what the user on Math Exchange was seeing are two unrelated pieces of number theory, but illustrated in one drawing. The first is that 44/7 is a very close rational approximation for 2 pi, which results in the residue classes mod 44 being cleanly separated out. The second is that many of these residue classes contain 0 prime numbers, or sometimes just 1, so they won't show up. But on the other hand, primes do show up plentifully enough in all 20 of the other residue classes that it makes these spiral arms visible. And at this point, maybe you can predict what's going on at the larger scale. Just as 6 radians is vaguely close to a full turn, and 44 radians is quite close to 7 full turns, It just so happens that 710 radians is extremely close to a whole number of full turns. Visually, you can see this by the fact that the point ends up almost exactly on the x-axis, but it's more compelling analytically. 710 radians is 710 divided by 2 pi rotations, which works out to be 113.00000095. Some of you may have seen this in another form. It's saying that 710 113ths is a close approximation for 2 pi, which is more commonly seen in saying that 355 over 113 is a very good approximation for pi. Now, if you want to understand where these rational approximations are coming from, and what it means for one like this to be unusually good, like way better than you would get for phi or e or square root of 2 or other famous irrationals, I highly recommend taking a look at this great Mathologer video. For our storyline, though, it means that when you move forward by steps of 710, the angle of each new point is almost exactly the same as the last one, just microscopically bigger. Even very far out, one of these sequences looks like a straight line. And of course, the other residue classes mod 710 also form these nearly straight lines. 710 is a big number though, so when all of them are on screen, and there's only so many pixels on the screen, it's a little hard to make them out. So in this case, it's actually easier to see when we limit the view to primes, where you don't see many of those residue classes. In reality, with a little further zooming, you can see that there actually is a very gentle spiral to these. But the fact that it takes so long to become prominent is a wonderful illustration, maybe the best illustration I've ever seen, for just how good an approximation this is for 2 pi. Tying up the remaining loose thread here, if you want to understand what happens when you filter for primes, it's entirely analogous to what we did before. The factors of 710 are 71, 5, and 2. So if the remainder, or residue, is divisible by any of those, then so is the number. When you pull up all of the residue classes with odd numbers, it looks like every other ray in the otherwise quite crowded picture. And then of those that remain, these are the ones that are divisible by 5, which are nice and evenly spaced at every fifth line. Notice, the fact that prime numbers never show up in any of these is what explains the pattern of the lines we saw at the beginning coming in clumps of 4. And moreover, of those remaining, these 4 residue classes are the ones that are divisible by 71, so the primes aren't going to show up there. Divisible by 71, so the primes aren't going to show up there. And that's what explains why the clumps of 4 that we saw occasionally have like a missing tooth in your comb. And if you were wondering where that number 280 came from, it comes from counting how many of the numbers from 1 up to 710 don't share any prime factors with 710. These are the ones that we can't rule out for including primes based on some obvious divisibility consideration. This, of course, doesn't guarantee that any particular one will contain prime numbers, but at least empirically, when you look at this picture, it actually seems like the primes are pretty evenly distributed among the remaining classes. Wouldn't you agree? This last point is actually the most interesting observation of the whole deal. It relates to a pretty deep fact in number theory, known as Dirichlet's theorem. To take a simpler example than residue classes mod 710, think of those mod 10. Because we write numbers in base 10, this is the same thing as grouping numbers together by what their last digit is. Everything whose last digit is 0 is a residue class, everything whose last digit is 1 is another residue class, and so on. Other than 2, prime numbers can't have an even number as their last digit, since that means they're even. And likewise, any prime bigger than 5 can't end in a 5. There's nothing surprising there, that's one of the first facts you observe when you learn about prime numbers. Anything bigger than 5 has to end in either a 1, a 3, a 7, or a 9. A much more nuanced question, though, is how exactly these primes are divvied up among those remaining 4 groups. Here, let's make a quick histogram, counting through each prime number, where the bars are going to show what proportion of the primes that we've seen so far have a given last digit. So, in particular, the 2 and the 5 slots should go down to 0 over time. What would you predict is going to happen as we move through more and more primes? Well, as we get a lot of them, it seems like a pretty even spread between these four classes, about 25% each. And probably that's what you would expect. After all, why would prime numbers show some sort of preference for one last digit over another? But primes aren't random, they are a definite sequence, and they show patterns in other ways, and it's highly non-obvious how you would prove something like this. Or, for that matter, how do you rigorously phrase what it is that you want to prove? A mathematician might go about it something like this. If you look at all the prime numbers less than some big number x, and you consider what fraction of them are, say, 1 above a multiple of 10, that fraction should approach 1/4 as x approaches infinity. And likewise for all of the other allowable residue classes, like 3 and 7 and 9. Of course, there's nothing special about 10. A similar fact should hold for any other number. Considering our old friends the residue classes mod 44, for example, let's make a similar histogram, showing what proportion of the primes show up in each one of these. Again, as time goes on, we see an even spread between the 20 different allowable residue classes, which you can think of in terms of each spiral arm from our diagram having about the same number of primes as each of the others. Maybe that's what you'd expect, but this is a shockingly hard fact to prove. The first man who cracked this puzzle was Dirichlet in 1837, and it forms one of the crowning jewels at the foundation of modern analytic number theory. Histograms like these ones give a pretty good illustration of what the theorem is actually saying. Nevertheless, you might find it enlightening to see how it might be written in a math text, with all the fancy jargon and everything. It's essentially what we just saw for 10, but more general. Again, you look at all of the primes up to some bound x, but instead of asking for what proportion of them have a residue of, say, 1 mod 10, you ask what proportion have a residue of r mod n, where n is any number, and r is anything that's co-prime to n. Remember, that means it doesn't share any factors with n bigger than 1. Instead of approaching 1/4 as x goes to infinity, that proportion goes to 1 divided by phi of n, where phi is that special function I mentioned earlier that gives the number of possible residues co-prime to n. And in case this is too clear for the reader, you might see it buried in more notation, where this denominator and the numerator are both written with a special prime counting function. The convention, rather confusingly, is to use the symbol pi for this function, even though it's totally unrelated to the number pi. In some contexts, when people refer to Dirichlet's theorem, they refer to a much more modest statement, which is simply that each of these residue classes that might have infinitely many primes does have infinitely many. In order to prove this, what Dirichlet did was show that the primes are just as dense in any one of these residue classes as in any other. For example, imagine someone asked you to prove that there are infinitely many primes ending in the number 1, and the way you do it is by showing that 1/4 of all the primes end in a 1. Together with the fact that there are infinitely many primes, which we've known since Euclid, this gives a stronger statement, and a much more interesting one. Now the proof, well, it's way more involved than would be reasonable to show here. One interesting fact worth mentioning is that it relies heavily on complex analysis, which is the study of doing calculus with functions whose inputs and outputs are complex numbers. Now that might seem weird, right? I mean, prime numbers seem wholly unrelated to the continuous world of calculus, much less when complex numbers end up in the mix. But since the early 19th century, this is absolutely par for the course when it comes to understanding how primes are distributed. And this isn't just antiquated technology either. Understanding the distribution of primes in residue classes like this continues to be relevant in modern research too. Some of the recent breakthroughs on small gaps between primes, edging towards that ever-elusive twin prime conjecture, have their basis in understanding how primes split up among these kinds of residue classes. Okay, looking back over the puzzle, I want to emphasize something. The original bit of data visualization whimsy that led to these patterns, well, it doesn't matter. No one cares. There's nothing special about plotting p, p in polar coordinates. And most of the initial mystery in these spirals resulted from the artifacts that come from dealing with integer number of radians, which is kind of weird. But on the other hand, This kind of play is clearly worth it if the end result is a line of questions that leads you to something like Dirichlet's theorem, which is important, especially if it inspires you to learn enough to understand the tactics of the underlying proof. No small task, by the way. And this isn't a coincidence that a fairly random question like this can lead you to an important and deep fact from math. What it means for a piece of math to be important and deep is that it connects to many other topics. So even an arbitrary exploration of numbers, as long as it's not too arbitrary, has a good chance of stumbling into something meaningful. Sure, you'll get a much more concentrated dosage of important facts by going through a textbook or a course, and there will be many fewer uninteresting dead ends. But there is something special about rediscovering these topics on your own. If you effectively reinvent Euler's totient function before you've ever seen it defined, or if you start wondering about rational approximations before learning about continued fractions, or if you seriously explore how primes are divvied up between residue classes before you've even heard the name Dirichlet, then when you do learn those topics, you'll see them as familiar friends, not as arbitrary definitions, and that will almost certainly mean that you learn it more effectively.
Alright, so when people are using Fibonacci and primes and all that stuff to define patterns on their chart, they're trying to figure out that theorem, okay, the Dirichlet's theorem. And I find it so fascinating people don't understand. Like, they see it, they can understand, or they understand it, but they don't see it. They don't know what it is. Well, there it is. That's why you use pi and all that stuff in charting as well. I'm gonna pause the video for a little bit. Okay. Alright, so concluding this part of the video, I'm just gonna leave it again with this up on the screen. So again, what you're doing with your indicators is you're defining certain principles of wave functions. Okay? And I advise you to revisit your EMAs and start understanding how those actually work, rather than just, oh, the golden cross. Just, you have to learn what your indicator is actually doing in order to understand the relationship behind it. This was Kai Buzz. Stay fresh, stay out of trouble, trade safely, and I will get back with a part 2 of describing wave functions and how my indicator works. Oh, I am so sorry. I almost forgot to go back over and cross-reference. Okay, so again, the estimated moving averages are a single wave function that go through the center on a certain axis, right? Okay? If you're following the video, is a center line around the axis, okay? Then when we look at something like this, because I have to build it in parts, can't just put it all together in one, you know? So now this would be the money flow oscillator, right? Right here is like the visual representation of money leaving and entering the market, right? Just for a little bit of information about this, it is inverted, because this is really confusing. Like, to me, like, if you have it this way, it confuses me, so I have to invert it for it to display right to me, and it makes more sense to me. to invert the scale, and like this right here would be a buy because that would be money going into the market, and then money leaving the market, money coming into the market, money leaving the market, money coming into the market, money leaving the market, and so forth and so on as you go through the oscillator, right? So money leaving the market to a sell off, okay, right? Or money, I'm sorry. All right, so I gotta restart. All right, so this is a sell point, right? This is money coming into the market, and then boom, it goes up, right? And then as soon as the line flips, that means money is leaving the market, okay? And then it oscillates back to where money is going to enter the market, and then we see a quick pump followed by money exiting the market, okay? And then money entering the market, money exiting the market, money entering the market, or yeah, entering the market, money exiting the market, money entering the market, money exiting the market, money entering the market, money exiting the market, money entering the market, money exiting for a quick sell off in between those candles, and then entering, and then sell off, and then boom, boom, and then money entering, and then boom, down, exiting, and then so forth and so on. And that's how the wave function works. Like right now, we're looking for money entering the market, so this should be flipping downwards. The bar count is a little messed up. Like again, I'm building this on Pine Editor. I can't get it correct. If I were to have these lines defined even better, these would be more of peaks. And I would try to get the inner peaks as well a little better. But um, yeah, I can't really do that with Pine Editor. I'm stuck with like very little code options. Um, then this one is a multi-layered type. So let me close this one. Let me get these EMAs off. Or no, I'm gonna leave them. Alright, so we're on Bitcoin, right? If we're looking at this indicator, this is more of a complex kind of indicator. So I don't even know how. So the orange line is Bitcoin dominance, right? The red line are inner sales on the alt. So this is coming down to the sphere of the market, the hypersphere of the market, right? So I have to be able to measure um, different things within the market, and it's all a part of the same hypersphere, right? So I have to be able to include the information of the altcoins within the hypersphere of Bitcoin to get these momentary false signal sell-offs. And really, we're looking at the orange line right here as the movement line for Bitcoin, paired with the let me make it a little bigger, paired with the red moving line as well in the signal, okay? So this is like trying to, still, I don't have pi on here yet. I'm still trying to figure if I can even do that kind of make Pine Editor make that fucking equation, because I would probably break the coding on fucking Pine Editor. Um, that's the difficult part, but this is the interesting part. So when I switch over to an altcoin, oh, I gotta hold on. Let me load the money flow oscillator. I shouldn't have deleted that. Okay, sorry about that. All right. So what this is displaying is cell signals pretty much. So when you have these two red line cross at the top, you have a cell, right? Cell, cell, and then repeated cell. So cell, because we had a a um a three a fucking a quad a a, a fucking a six function cancel or cell signal within one movement right here. So one, two, three, or four, two, four, five. Sorry, five function cancellation right here, right? And then we had a cell off, and then so forth. We have a four cancellation, a one cancellation, another cancellation, and then another cancellation. So the altcoin market is much more volatile. So you get a lot of false signals from Bitcoin. That's why when I flip to Bitcoin, you know, I have to be able to display the information a little differently to be able to interpret it. Because we're looking at a multi-dimensional fucking equation of things, and I still got a few more layers to add on to it. So if we overlay this real quick, and again, I have to invert it, because then it makes much more sense. Alright, so when we add these two pieces of the equations together, we get this. So we've got a buy signal and the market goes up. Alright, now watch this. So let's just start from here. Buy, sell. A cancellation and then a buy signal, which would cancel this signal out, right? If the market's going to dump a bunch of money into the market, it's going to cancel that sell and it's going to revert up, right? And that's why we see this pump right here. And then we go into a sell signal right here. All right. And then we have a buy signal. The market goes up. On that candle, once the market goes up, we have a sell signal. Continuing on, we have a buy signal after the sell signal, and then we have the market revert up. Then we get money in flux from here, right? And the market trades up. We get our first indication of downwards momentum by having a three function cancellation. Then we have a sell off, and then somewhere in between here on the smaller time frames within the whole hyper multidimensional sphere that we're plotting here, we have another buy, and then you see the market go up, but then we have a sell off right after that green candle, and then we have a buy signal, the market trades up, and then a sell signal, market trades down, and then again within the sphere. So let's go to May 14th to 16. And I'll show you what I mean. So let's go to a 2-hour. So we're on the 4-hour, by the way. So May 16th, 16. So here we see what is going on a smaller time frame. Okay, and this is all the market is doing, is trading. So when we get a buy signal over a red signal, that's usually a cancellation of negative momentum, but that was canceled, and then that moved into a move higher followed by a sell signal, and this would be more of like a small time frame kind of sell, and then we would have to zoom in further into the hyper, whatever you want to call it, to see the smaller time frame cells, right? So we're zooming out to a larger plane when we go to the 4 hour, when we go to the day, and we get less noise and better information on swing trading. Here we had, a buy signal and then, money influx. The market trades up, and then on the final curve after the cancellation, double cancellation, we have a little bit of a dump, followed by a buy and a cancellation of a sell signal, or negative momentum into positive momentum, followed by influx of money, pumping the market, and then dumping the market. Buying the market, dumping the market. Buy, dump the market from on a smaller time frame, and then we start trading downwards. And I don't have the actual EMAs that I use on here, but I'll get on that here in a second. I'm gonna leave the money flow and everything up, so I'll be right back. Alright, and so I got the other part of my indicator loaded. So let me hold on one second. Okay, I'm so sorry about that. Alright, so going further into topic on how my indicator works is I'm gonna go back to Bitcoin just so that way I can show you Bitcoin is a much more difficult display again to read. So I'm in this sphere, in this part of the sphere that's being displayed right here. I'm looking for the orange and red line crosses above two and within each other, and then above and below the white signal or market moving average oscillation, right? So here we can see that the market's trading upwards right now, which is cool. By the white line, Bitcoin's dominance went down. The money left Bitcoin. So think of it as this. Like, okay, if money starts flowing into Bitcoin, we're gonna get a pump, right? So this is money entering Bitcoin, okay? Then this is money exiting Bitcoin, and that's why we have that sell signal, right? That cross, that red, okay? So, and then again, we have, money start entering the market right here. A little further back, it's again not perfect, but it's meant to give a rotation. And then, so you got a buy, and then Bitcoin's market cap goes up, and we got Bitcoin moving up in price. And then we're looking at a drop right here. You see a little flinch up on the daily, okay? And that's why we're going to see a drop in Bitcoin here in 5 hours on May 18th or May 20th into May May 18th into May 19th. We're going to see a drop in price in Bitcoin if that flips bearish, okay? And we can pull this down and look at the cloud is painting that there is a rotation in sell volume. So now this is going to rotate up more than likely on the daily. And going further in detail, most of these all these lines are EMAs and SMAs, which are what again? The wave functions, right? The wave functions, okay? So, I'm still trying to figure out if I like this setup or not. I really haven't settled on it. I know I like the white band right here when Bitcoin paints top targets and then it paints bottoms. I love that. But as far as um, how it's displayed, I don't know if I like that. And then this cloud here is, um, again, a double a wave function of two lines that coincide and then when they cross and shit, right? So that's the basis of how an indicator and how my chart indicate works. I'm still trying to figure out if I got a good enough model here. I think I could do better, but it's the problem with coding on Pine script. It's just not very capable of what I wanted to do. So if I can figure a way out to make it work without breaking everything, then I'm set. And that's what I'm doing right now. So I'll get back to you, everybody that wasted their time and lives watching this video. Um, Thank you very much for watching it, and have a good night or day or whatever.